Yes, good afternoon all. Let's start the class.
Yes, sir. Good evening, sir.
Right. Yeah, in continuation to the about our morning topic is that we are discussing about the determination of general properties of alkalides and structure determination, general methods of structure determination of alkalides. In that last part, degradation experiments. Degradation of natural products. Generally, these degradation experiments will give the information about the type of heterocyclic system. That is, especially the nitrogen is present in the nitrogen heterocyclic system. Right. Nitrogen heterocyclic ring present in the alkylides or cleaved at carbon nitrogen bond, and the nitrogen is eliminated from the ring. The resulting acyclic segment is identified. If nitrogen is in the heteroaromatic ring system, the degradation experiments are somewhat difficult. Okay. For that, we need to get a saturated nitrogen heterocyclic system by simple reductions. Okay. Then, after getting the saturated heterocyclic containing alkaloids, then we are subjected to various kinds of degradation experiments, in which the important degradation experiments are the first one, Hoffman. Hoffman exhaustive methylation. Hoffman exhaustive methylation. This is called HEM method. Hoffman exhaustive methylation. The second one is MD method. MDIS method or MDIS degradation. And the third one is Van Braun degradation. Van Braun degradation. Van Braun degradation. In the Van Braun degradation, we have other we have to classify into two ways. That is Van Braun cyanogen bromide degradation, cyanogen bromide degradation, and the second one is Van Braun for secondary amines, cyclic secondary amines degradation. Van Braun for cyclic secondary amines degradation. These are the generally appearing degradation for knowing the structure of the alkalides. Okay, then coming to the first one, hem degradation or Hoffman exhaustive methylation degradation. Hoffman Hoffman exhaustive methylation is called it as hem degradation. In this experiment, first you take the heteroaromatic uh, alkylide. Suppose the alkylide containing the heteroaromatic, you cannot directly do the hem. First, we need to convert it to saturated systems. That means first you take if pyridine-like structure is present in the alkylide, pyridine-like structure is present in the alkylide, then it is subjected to the reduction, granulated dehydrogenation. Then it leads to the formation of saturated heterocyclic, right? After the formation of saturated heterocyclic, it contains the secondary amine. Then it is treated with methyl iodide, methyl iodide. Then N-methylation takes place. Then it forms a quaternary ammonium salt. The positive charge is there. This will be stabilized by the iodide ion, right? Then it will be treated with silver hydroxide, AgOH. Then the iodine is replaced by hydroxide ion, OH minus. Then whenever it is having, this is the alpha position, this is the beta position. At beta position, if it is having hydrogen, there is a elimination of that hydrogen ion or water molecule, that right, OH minus ion and H plus both combine to get water is eliminated on heating. That leads to formation of opening of that ring. That leads to formation of a double bond here, and a tertiary amine will be generated. Okay. But from the quaternary ammonium salt to it converts to tertiary amine. Further, this is the first step of first Hoffman exhaustive methylation. Up to that hem. From here to here, this method is called hem. Again, we need to perform the second step of second hem procedure. Again, you are treated with methyl iodide. Up to this, hem is completed. Again, we are starting second hem. This is the first hem and the second hem. Two times we are conducting the hem, right? Again, it generates the quaternary ammonium. 'Ammonium 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 CH3, CH3, CH3 plus charge, the iodide minus. Right. Then you are treating with silver hydroxide, AgOH. OH minus. Right. Again, it is having the beta hydrogen, alpha beta position. Then elimination of proton. This proton is combined with OH minus that leads to the formation of water. Water is eliminated on heating. Then it leads to the formation of this, and along with trimethyl, trimethylamine will be generated. Right. Now this method is called HEM. Heterocyclic is reacting with methyl iodide to give the solid quaternary ammonium salt, quaternary ammonium iodide. It is on treating with AgOH to give rise to a corresponding quaternary ammonium hydroxide. It is on heating to give the one double bond and water. Then water. Then it is carrying to carry out the HEM. It is required to. It is the mandatory thing is the molecule should have beta hydrogen. Beta hydrogens. Therefore, to carry out the hem, it is the mandatory thing. Okay. After the one hem is done in this particular molecule, a double bond is generated along with the tertiary amine is generated. Ammonium amine is generated. Later, it will be conducted to the second hem. Then it leads to the formation of this unsaturated system. This unsaturated system containing 5 carbons, right? 1 comma 4, 1 comma 4, pentadiene. Pentadiene. One of the nitrogen it is also the part of ring, therefore it is including by combining these 5 carbons. Therefore, that ring size is the 6-membered. It indicates the 6-membered ring is present in that system. Right. Suppose we are going to conduct it on the that hem method is conducting on the quinoline. First, you are going to conduct the another simple system. If it is the alkaloid is containing with the 5-membered ring, that is a pyrrole is containing in that molecule. When we are these unsaturated aromatic systems are not at all not possible to conduct the HEM method. Then first you need to convert into a saturated ring system by reduction. Then it leads to the formation of saturated pyrrolidine. Right. Then it is conducted a methylation with the methyl iodide, 2 moles of methyl iodide. Then it leads to the formation of N-N-dimethyl, N-N-dimethyl, N-N-dimethyl iodide, imines. This is the quaternary ammonium iodide salt. Then it is treated with AgNO3, sorry, AgOH. That leads to the formation of N-N-dimethyl quaternary ammonium hydroxide, OH minus. Then it is treated with, it is on heating, then alpha, this is the beta position, then elimination of proton, simultaneously cleavage of carbon-nitrogen bond, then that leads to the formation of a double bond between the C2 and C3, and nitrogen, it is existing as a tertiary amine. Tertiary Again, I'm going to treating it with the methyl iodide. Methyl iodide. This is the quaternary ammonium salt. Again, it is formed quaternary ammonium iodide salt is generated. Again, we are going to connect the reaction with silver hydroxide. Then iodine is replaced. That AgI becomes precipitate in the both the cases. AgI is the precipitate is obtained along with the quaternary ammonium hydroxide. OH mix. Right. Here double bond is there. Again, it is the alpha position. It is the beta position. It is having hydrogen. Therefore, it will be eliminated as H plus ion. This H plus ion and OH minus combined together, that leads to formation of water. Water is eliminated. Then it leads to formation of alpha beta unsaturated carbonyl compound. This is 1,3 butadiene along with trimethyl amine. A tertiary amine will be generated. Then the formation of this 1,2, 1,3 butadiene indicates that the alkaloid is having or existing with the 5-membered heterocyclic nitrogen heterocyclic system. Right. Then hem of isoquinoline. This is suppose if you are taking the first one is the pyridine, the second one is the pyrrolidine, then the third one is hem of isoquinoline. Isoquinoline. What is that isoquinoline? This is the isoquinoline. Now it is treated with the sodium ethoxide, so or sodium methyl alcohol, sodium methyl alcohol. Then it will be undergoing the partial reduction of the both the rings. That means one of the ring will be completely reduced. That leads to the formation of a partially saturated isoquinoline. That is 1, 2, 3, 4 tetrahydroisoquinoline. 1, 2, 3, 4 tetrahydroisoquinoline. Then it is subjected to methylation. 2 molecules of methyl iodide in presence of DMS. Then it leads to the formation of CH3, CH3 plus iodide minus. That is the quaternary ammonium iodide salt will be. It is a crystalline solid. Then it is alpha position and it is the beta position. At beta position, it is having the hydrogen. Then it will be distinct. It is treated with AgOH. Right. This hydroxide ion, quaternary ammonium hydroxide is generated. Then elimination of that beta hydrogen has H plus ion. Simultaneously, this OH minus and H plus will combine on heating. That leads to the water vapor will be evaporated. Then once this will be during the elimination, this carbon nitrogen bond will be eliminated, detached or cleaved. Then it leads the formation of again. This is the tertiary amine. Tertiary amine is generated, but further there is no hem is possible. Other the second hem, only one hem is possible. The second hem is not possible in this case. The second hem up to this one is the first hem. From this onwards, second hem is not possible. Therefore, isoquinoline gives only one hem degradation. The second hem degradation is not possible. This is about the hem, Hoffman exhaustive methylation. Based on the Hoffman exhaustive methylation, we can identify the what kind of heterocyclic nitrogen heterocyclic, whether it is a pyridine or quinoline or isoquinoline or pyrrolidine may be present in the alkaloid. Based on the analysis, we can find out. Okay. Then next one is MD's degradation. MD degradation. This MD's degradation in the first one is the condition is hem Hoffman exhaustive methylation requires beta hydrogen, but MD degradation it is not required beta hydrogen. That means even it is when the beta hydrogen is absent, we can conduct the degradation. That is called MD's degradation. This degradation is helpful when beta hydrogens are absent. Most of the cases we are going to conduct the hem when beta hydrogens are available. If the beta hydrogens are absent, then you need to choose this MDs are absent in the nitrogen heterocycle. Then we can choose two methods. Suppose we are going to take the quinoline. The quinoline may be present. Suppose quinine containing the quinoline. When the quinine is containing quinoline, can be identified by these MDs are Hoffman degradation method. Okay, but here the method one, in the method one, how we can conduct this method in two ways. Method one, this is treated with ethanol in presence of sodium. The sodium ethanol reduction. Then it is the formation of a partially reduced structure that is 1, 2, 3, 4 tetrahydroquinoline that will be generated. Then it is treated with the 2-methyl iodide. Then it is the formation of a quaternary ammonium iodide salt is generated. Then it is treated with the sodium amalgam. When it is treated with the sodium amalgam in ethanol, then it leads to the formation of elimination of HI, that leads to the breakage of this bond, breaking of this bond. Then it gives the product. The test second test amine again it will be generated. Again, up to this is the MD's method. But here it is the possibility it is having the beta hydrogen is present. Then in such case, it is treated with 2-methyl iodide again. Not require the 2-methyls. Just one require one methyl iodide required. That is it is treated with methyl iodide. Now it is treated with AgOH. OH minus. Right. Then on heating, elimination of water, then it leads to the formation of this CN bond will be cleaved. That leads to the formation of this compound along with the tertiary amine. Tertiary amine. Yeah. This is the method 1 for the quinol. If you take the isoquinol, method 2, we are taking here isoquinol. Again, it is treated with the sodium in ethanol. Then it leads to the formation of partially saturated rings. This is 1, 2, 3, 4 tetrahydro isoquinol. Tetrahydro isoquinol. Right. It is treated with the methyl ion, right? A positive charge, it is linked with the iodide salt. That means quaternary ammonium iodides. Okay. Then here you have the two possibilities. You may conduct the hem, you may be conduct the hem, or you may be conduct the MD. We conduct the MD. First, you conduct the hem. Hem means it is having beta hydrogens. Therefore, beta hydrogens are there. Then it is treated with the AgOH. Then it is converted into corresponding OH lines, right? Then, which is on heating, elimination of water. Then the ring opening this takes place. This carbon nitrogen bond will be broken down. This beta hydrogens will be related to this. Then it leads to the formation of will be generated, right? Suppose if it is, later I will tell you. Then here in this step, we are going to conduct the MDs. For conducting MDs, what we need to do? It is again treated with sodium, sodium amalgam in ethanol. Sodium amalgam in ethanol. Then what's happening? This bond will be broken down. Directly we are connecting. This bond will be broken down. Then it leads to the formation of the sodium amalgam is used as a reducing agent, hydrogenating agent. Then this will be generated. Right. Now it is having beta hydrogens. Then you can conduct the hem analysis. Next, hydrogen of an exhaustive methylation. That beta hydrogen will be first it is treated with methyl iodide, and second it is treated with AgOH. Third one, if you are heating, then that beta hydrogens will be eliminated as water molecule along with the hydroxide. Then it leads to the formation of along with the tertiary amine, NNN trimethyl ammonia. Again, here it is, if we are conducting here MDs, then this bond will be broken down. How it is, first you are conducting with the treating with methyl, right? And second one, if you are going to treat with sodium amalgam in ethanol, then it leads to the formation of this one. Both are same, but we are changing the sequence for understanding. Both will give the same. Right? Here also trimethyl amine will be generated. That is the MD's degradation. Only MD's degradation is helpful when the beta hydrogens are absent and the heterocyclic ring which is present in the alkaloid. Next, coming to the Van Braun degradation. Van Braun degradation. The first one in this Van Braun cyanogen bromination degradation. Van Braun degradation. It is specific for tertiary amines. When tertiary amines are present, no need to conduct the methylation. Then directly we can subject it to this degradation. Tertiary amines. It is specific for the tertiary amines. The cyanogen bromination method is helpful for the compounds which are not degraded by the M method, M and M method. When this method is applied, when the alkaloid degradation is not possible. Degradation is not possible with the hem and MDs. Degradation. MD degradation. How it will be conducted? I just take this a general example. Again, I am going to take the N-alkyl, N-alkyl piperidine. It is treated with the cyanogen bromide, cyanogen bromide. Then it leads to the formation of quaternary ammonium bromide salt, quaternary ammonium cyanogen bromide, cyanogen ammonium bromide. Cyanide will be here, gets the positive charge. The bromide will be stabilized. Then it is again treated with the HBr and on boiling that solution. Then it will be open this bond, right? It leads to hydrolyzing the carbon nitrogen bond. Then alkyl group and CN and bromination is takes place here. Bromination is takes place here, right? Then further, it is boiled in the dilute acid, boiled in the dilute acid. This cyanogen will be converting into, cyanoid group will be converting into its corresponding carboxylic acid. COH. After formation of this carbon dioxide, carboxylic acid, just boil it for the decarboxylation. For the decarboxylation. Then it leads to the formation of NHR, the group. Then formation of the secondary amino bromide derivative indicates that the size of the ring. Adjacent to the, you start the numbering with 1, 2, 3, 4, 5, and whatever the carbon which is attached to the bromine, that is the 6. Therefore, the alkaloid which is containing a 6-membered ring. You will get here. This is the 6-membered ring. Simply, you can find out the size of the ring and type of the heterocyclic ring. For example, I am taking the isoquinoline. Now, it is treated with the sodium in ethanol. This is the, then it is treated with the only 1 mole of methyl iodide. Then it leads to the formation of a tertiary amine, CH3. Then it is treated with the cyanogen bromide. Then it is forms the N-cyane derivative. CH3, CN is the positive charged one, therefore it is the bromide ion. It is quaternary ammonium salt. Then it is boiled with the dilute HCl, dilute HCl. That bond will be broken down. That means this bond will be broken. Here the two possibility, it may break down this bond or this bond, but possibility is this one because highly stable benzoyl chloride will be generated, benzyl chloride will be generated instead of this one. This is the phenyl ethyl bromide will be generated. The stability when we compare the benzyl bromide is the more stable than the ethyl bromide. Due to that reason, this bond will be broken down. This will be there. You can see the right analogy. This, right? Then it is first one treated with the dilute acid in water, followed by heating for the decarboxylation. Then it leads to the formation of a secondary amine and bromine. From this, you can find out the structure, ring size of the heterocycle and what kind of heterocycle present in it. Okay. Next one, Van Braun method for secondary cyclic amines. Cyclic amines. Van Braun method for secondary cyclic amines. Now, you take the same piperine. This is the secondary amine. When it is treated with benzyl chloride, C6H5COCl, benzyl chloride, then it leads to the formation of N-benzylation is this C6H5. Right. It is treated with bromine phosphorus tribromide, Br2, PBr3. Then whatever the C double bond is gets brominated. Simply take it C6H5. The double bond will be converted into dibromolecular. Then it is conducted the distillation under reduced pressure. Distillation under reduced pressure, that is vacuum distillation. Then it leads to the dibromo compound will be generated. That is 1, 2, 3, 4, 5. 1,5 dibromo pentane derivative will be generated along with cyanogen bromide, cyanogen C6H5Cl. That will be generated. Okay. The formation of this 1,5 dibromo product indicates the six-member ring is present. The nitrogen will be eliminated in the form of nitrate group. That is the cyanobenzene. Derivative generated in the cyanobenzene nitrogen is came from the cyclic system. Okay, these are the degradation experiment. Based on the degradation experiment, we can find out the type of heterocyclic or size of the heterocyclic can be found out. Okay, these are the degradation experiment. Now coming to structure determination of pepavarin. Structure determination of pepavarin. Structure determination of pepavarin. Yes. What is the source of that alkali? This is the pepavarin is the alkali. This pepavarin is isolated from the latex of Papaver somniferum. Venom seeds. Or it is also called This whatever the soon what is that plant? We call it as poppy or opium. In the our olden people called as Nalamundu, right? It is came from the opium. How many of you know the black uh, poppy seeds? గసగసాలు అంటాం బ్లాక్ నల్లని గసగసాలు అంటాం ఓకే తెలుగులో ఎస్ it is poppy plant or opium plant. Whenever it is ripe, it gives a flower bud. When you cut that flower bud, it gives the latex. From that latex, we have find out several alkaloids. This latex contains several alkaloids. That is, it contains the morphine, codeine, thebaine, and and some pepavin. It's whatever we are going to discuss about now. Pepavin. Okay, four kinds of alkaloids present. Okay, it is the highly intense a narcotic drug because it is having four kinds of products. All four are highly biological active. It will be what we call the relaxing agents. That's why sometimes it is uh, used for the pain management. Okay. Structure determining this papaver structure is determined by the papaver structure determined by the Goldsmith in 1983, 1888. Okay, by using the oxidative degradation method. Then what method is proposed? That method we are going to discuss now. Whatever the Goldsmith method is there, that Goldsmith method, how this method is elucidating the structure of papaver. We are going to discuss now. Coming to the elucidation, structural elucidation. Structural elucidation. For understanding the structure or for determining the structure, first we need the molecular formula. Molecular formula that is C20, H21, O4, N. C20, H21, O4, N. Then we take the papaver. This is the molecular formula of papaver is C20, H21, O4, N. That means it is having 4 oxygens, 1 nitrogen, and 20 carbons and 21 hydrogens. Then whatever the compound isolated from the plant, that is the papaver crude material or a pure form of material, is subjected to methyl iodide. It gives the quaternary ammonium salt. Quaternary ammonium iodide salt. Quaternary ammonium iodide salt. Here, for one equivalent or 1 mole of papaver consumes 1 equivalent or 1 mole of methyl iodide. That indicates that papaver is existing with tertiary amine. This indicates that papaver is existing with tertiary amine. Now we write the same 1 equivalent of papaver papaver consumes one equivalent of methyl iodide to produce quaternary ammonium salt. Quaternary ammonium salt. Therefore, it indicates that whatever the papaver containing nitrogen, that the nitrogen present in the form of tertiary amine. The form of tertiary amine. Next, third, this indicates that that nitrogen is present in the form of tertiary amine. Third one, papaver, it is subjected to G-cell method, that is, it treated with two hydrogen iodide, that is, it consumes the four equivalents of hydrogen iodide, that produces papaver. Its formula is C16, H13, NO4, along with four methyl iodides, which is treated with the silver nitrate. It deposits or precipitates 4 moles of. That means you are taking the 1 mole of papaver. It produces 1 mole of papaver along with 4 moles of methyl iodide. This with 4 moles of methyl iodide reacting with 4 moles of AgNO3, that produces the 4 moles of Ag. This reaction, this is the G-cell method to find out the number of OCH3 group present in that molecule. This G-cell method directly indicates that the molecule containing the 4 methoxy groups in its structure. Therefore, G-cell method indicates that G-cell method of O-methoxy group determination showed it has 4 OCH3 groups and demethylated compound is papaver. That is, the 4 hydroxy groups are there. Papaver. This is having 4 OH groups. Right. Next, fourth one, oxidative degradation of papaver with K-amino. Oxidative degradation of papaver with KMNO4. You take the papaver, that is the C20, H21, nitrogen, O4, C20, H21, and O4. It is existing with, from the above data, it is existing with 4 OCH3 groups and 1 tertiary nitrogen. nitrogen. Now it is treated with cold dilute KMnO4. Then it produces papaverinol. Papaverinol. The analysis of this papaverinol, it is existing with the molecular formula C20H21NO5. One of the oxygen is increasing. That means that oxygen generated as a OH, and the remaining groups are same. There is no change in the remaining. It is one tertiary nitrogen. Again, it is treated with the hot dilute KMnO4. Then it gives the formation of papaveryldi. Papaveryldi. This is the actual ketone. Whatever the hydroxy group generated here, that will be oxidized into ketone. Its molecular formula C20H19. That means two hydrogens are reduced, and O5 nitrogen. Then it is increasing, that OH group is converting into ketone, one ketone, right? And four methoxy groups, there is no change. Four OCH3 groups are there, and one tertiary nitrogen is there. One tertiary nitrogen is there. Then again, it is treated with another step. Uh, it is treating with hot dilute KMnO4. Then it will be oxidized. That whatever the keto group that becomes oxidized, that leads to the formation of papaverinic acid. Papaverinic acid. Its formula is C16H13 O17 O7N. Look at here. In the previous step, we have only 5 hydrogens. Here, another 2 hydrogens are increases. Another 2 hydrogens are increases, but the number of carbons and the number of hydrogens are reduced. Number of hydrogens are reduced. From the above sequence of reaction, we suggest that a papaver containing a active methylene group. Here, an active methylene group is there. That active methylene group is an oxidation. That will a hydroxy group is introduced in the first step. In this first step, it will be a hydroxy group is introduced. In the second step, again you are going to oxidize. That will be converting into ketone. After the formation of the ketone, in the third step, one of the carbon bond will be cleaved. One of the carbon bond will be cleaved. Then that leads to the yes. Um, right. Actually, it is the keto carboxylic acid. Sorry, it is the keto carboxylic. It is having uh, only two OCH groups and one keto group and two COOH group. That is the reason here the number of oxygens are gradually rapidly increases. Then there is no change in this ketone. In the somewhere else of the group that will be oxidized, that will generate the two COOH groups. Therefore, from the above sequence of reactions, suggest that papaver containing a active methylene group, it is oxidized to carbonyl group. The formation of ketone indicates that the active methane group is present. And another reaction, the papaver is conducted oxidation with cold KMnO4 that produces the papaverinol. That indicates whatever the first step, the formation of OH, that is further undergoing the oxidation that leads to the formation of papaverin that contains the keto group. In the above degradation experiment, papaverinol is a alcohol. Papaverinol is a alcohol, and papaverine and papaverinic acid have a keto group. In the oxidation of papaverine to papaverinic acid, an aromatic ring is subjected to oxidized. That is the reason it is formed the 2-carboxylic acid group. One of the any benzene rings. Suppose it is the oxidative degradation of aromatic substances. Suppose this kind of aromatic substance is there, right? These bonds are undergoing oxidation. These bonds are undergoing oxidation. Then that leads to the formation of 2-carboxylic groups. COOH, that aromatic ring may undergoes the oxidation. That leads to the formation of that dicarboxylic compound. Dicarboxylic compound, right? Then that clearly indicates that pepavarandin and pepavaranic acid have a keto group. In the oxidation of pepavarandin, that is the third step, whatever the pepavarandin is there, in the third step, have a keto, two pepavarandin to pepavaranic acid, and aromatic ring is oxidized with the loss of OCH3 group. Look at here. After formation of pepavaranic acid, two OCH3 groups are reduced. That means an aromatic ring is oxidized with the loss of OCH3 group and formation of two COOH groups. Two COOH groups. Right. The same thing you need to write in the above degradation experiment. Pepavarinol is a alcohol and pepavarandin and pepavaranic acid containing with a keto group. In the oxidation of pepavarandin to pepavaranic acid, an aromatic ring is oxidized with the loss of OCH3 and formation of two COOH groups. Next is another degradation method, that is second oxidative degradation method. Oxidative. The previous one is oxidative degradation method with dilute KMnO4. Here we are using concentrated KMnO. Oxidative degradation. Oxidative degradation of pepavarin with the concentrated KMnO4. You take the pepavarin. It is the C20H21 NO4, which is subjected to oxidation with the hot concentrated KMnO4 oxidation. It leads to the formation of four products. One is baricic acid. Baricic acid, its molecular formula is C9H10O4. And second one is metahemipenic acid. Metahemipenic acid. This is C10H10O6. And the third product, pyridine tricarboxylic acid. Pyridine tricarboxylic acid is C8H5O6 nitrogen. Or you can write like this as nitrogen O6. Right. And the fourth one, D. Dimethoxy isophenolene. Dimethoxy isophenolene carboxylic acid. Carboxylic acid. All these molecules structure, if we know, then we can find out the linkages of these four molecules. Then only we can get the final structure. Then only we can get the final structure. Okay. There is a four molecules are generated on the oxidative degradation of concentrated KMnO4 of pepavarin. That is valeric acid. Its the molecular formula is C9H10O4. Metahemipenic acid C10H10O6, pyridine tricarboxylic acid C8H5NO6, and dimethoxy isoquinoline carboxylic acid, that is C12H11, sorry, H11O4N, one single nitrogen atom, right? These are the four molecules are generated. Then every molecule structure we need to elucidate, then only we can find out the structure. First, we coming to the varetric acid, structure of varetric acid. A. Sorry, structure of varetric acid. Structure of varetric acid. It's a molecular formula C9H10O4, and when we subject it to the G cell method, that is, take the varetric acid, it is subjected to reaction with hydrogen iodide. Then it produces the 2-methyl iodide. Then it is reacting with two molecules of GNO3. It precipitated 2 moles of Ag. Therefore, it indicates that varetric acid existing with two OCH3 groups. Out of the four, the two OCH3 groups are present in the varetric acid, right? Next, third one, varetric acid varetric acid. It is subjected to diazomethane, CH3N2. It produces monomethyl ester. Monomethyl ester. The formation of monomethyl ester indicates that it is having only one carboxylic acid. Therefore, it indicates that the varetric acid is a monocarboxylic acid. Varetric acid is a monocarboxylic acid. What is the meaning of monocarboxylic acid? One COOH group is present. One COOH group is present. Next, this is the important step. Take the varetric acid. Varetric acid. It is degradation or decarboxylation with calcium oxide and heat. That means it undergoes a decarboxylation. That means only one carboxylic acid group is there that will undergo the decarboxylation. That leads to the formation of varetrol. This is the known structure. Varetrol is the known structure. In that, two OCH3 groups are adjacent to each other. That's its original name is orthodimethoxybenzene. Ortho-1,2-dimethoxybenzene or orthodimethioxybenzene. It is the known structure. This is a varetrol. It is ortho-dimethoxybenzene. Right. From this reaction, we know that the position of two OCH3 groups in the varetric acid but we do not know the position of carboxylic acid group. The position of the CH acid group is confirmed by synthesis, from its synthesis only. From this valeric acid, uh, that is the 3,4-dimethoxybenzoic acid, right? Uh, Formation of alkyl indicates that the two methoxy groups are adjacent to each other. But we are knowing the position of the two OCH2 group, but we don't know the position of the carboxylic acid. That means the valeric acid is valeric acid is this is the partial structure OCH3 and OCH3, and along with the one carboxylic group acid. But we don't know the position of COH. That position is confirmed by its synthesis only. Confirmation is only by its synthesis only. Then what is the synthesis? Starts with uh, 4-hydroxy carboxylic acid, para-hydroxy benzoic acid. It is treated with concentrated H2SO4. Then COH. The sulfonation takes place, SO3H. A sulfonic acid is generated. Then it is treated with potassium hydroxide. Then it leads to the formation of 3,4-dihydroxybenzoic acid. This is treated with the methyl iodide in sodium hydroxide. That leads to the formation of valeric acid. This valeric acid, whatever we synthesize it and whatever we are isolated from the degradation products, both are same. Therefore, finally, the structure of valeric acid is the four OCH3 groups of pepavarin is present in the two OCH3 groups in the valeric acid. But the pepavarin is not having COOH. And we are discussing the structure of pepavarin. There is no indication for the presence of COOH group. Therefore, that COOH group may be the group which is generated from the active methylene group. That is the a junction point between the valeric acid and other species which are present in that molecule. Therefore, we can write one sentence here. In four OCH3 groups, pepavarin, two OCH3 groups are present in valeric acid, but pepavarin is not having COOH group. It is formed by the active methylene group. Active methylene group, which is it is formed by the active methylene group, which is the structural segment is oxidized to give valeric acid. Give valeric Variable acid. That is, if you believe it is a peptide, uh, this is the active methylene group. This is the structural segment, an important segment that leads to the formation of valeric acid on the oxidation, which is treated with hot, concentrated KMnO4 that leads to the formation of valeric acid. OCH3, OCH3. Okay. This is the structure of valeric acid. It is also confirmed by its synthesis. Next, metahemipenic acid. We have only 5 minutes time. I have second year class. Okay, don't worry. We'll complete the meta up to metahemipenic acid. Then we'll move to next part in the next week. Right? Into metahemipenic acid, structure B. I will move in some rapidly. Please understand. Okay. Metahemipenic acid. In this metahemipenic acid, what is the molecular formula? Molecular formula of a metahemipenic acid is C10H10O6. Then apply the G cell method for identify the number of OCH3 group. Metahemipenic acid. Metahemipenic acid is subjected to the G cell method. It produces the 2 moles of silver iodide precipitate. Silver iodide precipitate. Therefore, it indicates the presence of 2 OCH3 groups. 2 OCH3 groups. Then third one, this metahemipenic acid. Acid subjected to decarboxylation with calcium hydroxide. Decarboxylation. It produces the varitol. Varitol structure is already known. That is what is the varitol structure? Then OCH3, OCH. It is therefore metahemipenic acid is also the having the same varitol structure, but whenever this metahemipenic acid is treated with acetic anhydride. Acetic anhydride. First, you treat it with the diazomethane, CH2N, CH2N2. This is the esterification step, actually. Esterification. Then that leads to formation of dimethyl ester. Methyl dimethyl ester. That means the 2 carboxylic acids are there. The 2 carboxylic acids are generated corresponding methyl esters. Corresponding methyl esters. Therefore, it indicates the presence of 2 carboxylic groups. Therefore, it indicates the presence of 2 COOH groups. 2 COOH groups. Then, another reaction, fifth one, metahemipenic acid. Metahemipenic acid is subjected to boiling in acetic anhydride. This is the dehydrating agent. It leads to the formation of an anhydride. Anhydride. Anhydride means when the carboxylic acids are present in adjacent position and carboxylic acids groups are present in adjacent position, it loses the water molecule. Then it leads to the formation of an anhydride. An anhydride. Therefore, this reaction indicates that the two COOH groups are in the meta-hemipenic acid are adjacent position. Two COOH groups are present in adjacent position. Therefore, it indicates that the two COOH groups are adjacent positions. It may possible already bilateral structure is already existing in the meta-amylic acid. Therefore, in that two OCH3 groups are adjacent groups, and the remaining two OCH3 groups are also adjacent position. Based on that, there is a two possible structures. One is like this. One is the two COOH groups are like this, OCOH, and the two OCH3 groups are like this. This is the structure A. And another possibility is the COOH, and like this, OCH3, OCH3. This is the another structure. Okay. Suppose if you have taken this position, it will give the same B, structure A and structure B. Right. Then when metahemipenic acid is subjected to the monomethylation or monoesterification, two carboxylic acids are there. In that, I am going to connect only mono when metahemipenic acid is subject to monoesterification, that leads to formation of monoester. Only one kind of product will be generated. Only one isomer is generated. Only one isomer or one product, one unique product will be generated. How it is possible? Here, two structure A and structure B are there. What is the structure A? The structure A is like this. Whenever we are conducting monomethylation, OCH3, it is treated with one equivalent of diazomethane. Then it leads to formation of monoester. That is COOO, CH3, COOH, OCH. You substitute any carboxylic acid, the product is same. You are esterify this carboxylic acid or this carboxylic acid, gives the same product. Only one product will be generated. For example, you take this is the structure A. If you take the structure B, that is OCH3, OCH3 here, and COOH, COOH. Then we are applying the monomethylation. Look at here, it leads to formation of two products. One is the COOCH3, COOH, OCH3, OCH3, and you are going to conduct another methylation, the remaining carboxylic acid OCH3, OCH3, that we are specifically conducting the monomethylation, COOH, CH3. Look at here. Here the methylation takes place here, the first carboxylic acid, but here it is takes place. These are the two different products. These two, one and two are the different products. But here it produces the, even you are thinking this
Sir,
equation.
sir,
Yes, tell me.
that is meta-hemipenic acid. When
Yes.
it is going for, sir, on decarboxylation, means it contains when 2OCH3.
Mhm.
This is, sir, veratrol, sir.
I didn't get your question. Please repeat again.
जी sir. It is टिका डाल.
We are conducting the decarboxylation, na?
Yes, sir.
Already conduct na that lead reveals that already metahemipenic acid is having varicose structure. Due to that, we are only deciding that this in that metahemipenic acid also existing with the two OCH3 groups at adjacent position. That is the one of the evidence for the positions of OCH3 groups.
Yes, sir. Yes.
Okay. If you are conducting decarboxylation, we cannot find the COH positions. The COH positions are identified by the only this dehydration. We are treating with acetic anhydride, it produces the anhydride. The formation of anhydride is only possible the COH group. Both the COH groups are adjacent to each other. Then both are undergoing dehydration, that means removal of water, that leads to the formation of an anhydride. The anhydride formation is only possible. These two COH groups are adjacent to each other. Adjacent to each other. Right? I think, yeah, based on this reaction, the structure of
Yes, yes, sir. Thank you, sir.
the structure of hemipenic acid is based on all the above factors. Based on all the above factors, the structure of metahemipenic acid is following. That is structure A. Okay, it's structure A. What is the structure A? OCH3, OCH3, COOH, COOH. Okay, it is finally conformed by its synthesis. Finally conformed by its synthesis. Okay. Now I am closing the session. Your inorganics are waiting in the classroom, in Zoom class. You are joining to the inorganic link, right? Okay, I am closing the session. Sir is waiting for you. Do you have any doubt in the next, write it up in the Telegram group. I will give you the answers, or otherwise we will discuss in the next class. Okay. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.